So I wanted to give a bit of background on the parametric maps. So I'll start with this issue. I'm just going to share my screen. Can you see that, Joe?
Yep.
Perfect. Okay, so I posted this issue just a couple days ago. And one of the things that I was noticing is that, okay, so the way that we construct parametric maps, you need to have some way to approximate a step function. And so what we've done is we're using arctan functions, right? I mean, there's a whole bunch of different things you can use. Arctan is, we know the derivative, it's easy. So let's go with that. And so to create different structures and things like that, initially what I had implemented is that we just multiply these things together, right? So if you multiply a block, we have, 2 going in the horizontal directions and then 2 in the other directions. But the thing that I was encountering is that, like, you can see that that actually looks pretty funky if you soften the slopes, right? And why you want to soften the slopes is it helps.
Gradients.
Helps your gradients. And so this obviously is like just not really physical and not what we want to be inverting for. So there's a couple of options. I mean, one, like an ellipsoid is an easy thing to parametrize, but it is nice to also have a plate. And so what I've been looking at is actually changing, instead of multiplying these things together, defining it through, like, you think of the equation for a sphere. And so it's 1 minus, and then you have all the r squared terms, right? And so a square is actually just an approximation of the infinity norms. So you replace the 2 norms with infinity norms, and you get a square. And so what I've been working on is...
Sorry?
I
lost
that. This up.
The unit circle in infinity norm.
Yeah, so if I had just a 2 norm here, that's the equation for an ellipsoid, right? Mm. If you just replace that with the infinity norm, you get a square.
Right, L1 norm with diamond.
Yeah, and L1 norm
with
diamond.
Yeah, all right.
So if we have an infinity norm, it's a square. But obviously we don't want to actually use an infinity norm. So I've implemented an Ekblom norm. And so what that looks like is we have now, let me just start with this. Okay, so if we have a large P and a large slope, we get a square back, or a rectangle back. What's kind of interesting is the P, the norm value, actually controls like how round your corners are. So that softens the corners a bit. And if we go to 1, you get an ellipsoid. So that's kind of fun.
What slope again? Sorry.
So the slope, let me show you actually. So here, let's set this to slightly round the corners. So the slope is actually the slope on the arctan function. And so right now it's quite high. So if I reduce that, it blurs the edges. Does that make sense? So
where's the arctan? I thought we're not doing arctan anymore.
No, we're still doing arctan. So what we're doing is now we're just not multiplying them. What we are doing is, so here is our expression for a block. When this guy is below 0, we're outside the block. And when it's above 0, we're inside the block. Right? And so all we do is pop that inside of this guy, which is our approximation of an arctan function. And so anywhere that's outside, we're going to go to the value of the background, and anywhere that's inside, we go to the value of the...
Gotcha.
Does that make sense?
Yeah.
And so the slope there is this guy. And there's 2 ways I've tried to set it up for the user to actually interact with the slope. One is you can provide the exact slope. The other one is you can provide just a scale factor, and then it scales it by the smallest cell size in your mesh. because what, and Mike showed this in his thesis, and I've been playing around and I'm seeing the same thing, is that you want that change to happen over a couple cell widths, because that is just easier on your gradients. Whereas if you make it too sharp, it line searches like crazy.
And that depends on the dimensionality of your cells.
Yeah. Yeah.
So you scale your slope by your dimensions.
Yeah. Yeah. So you can either provide the slope, or right now I've called it a slope factor, which just scales it by the mesh. So it's the same idea, but in this case, it's easier to set sensible defaults on a slope factor than it is to set sensible defaults on just a slope. So then we can go ahead and derivative test that and make sure that that's all working. In a simple case, so even if I like crank this up, the derivative is still, I mean, you can see that it's less stable, right? And so that sort of does indicate that it's going to be harder to search. So I actually have a DC example where we can look at that, because it's on its own, the parametric, like, this isn't too crazy, but once you start pairing it up with other maps and exponentials and things like that, these tuning parameters really do matter. So what this example is we're doing a cylindrically symmetric simulation. We've got sorry, let me just see if I have a simple example of the model. Yeah. So we've got, this is a casing style example. So cylindrically symmetric, we've got a casing in the middle, and we've got a conductive target at depth, and it extends to a radius of 50 meters. So if I make this 80 example, you can see, so that's the conductive target that we're looking for.
Can you tell me, so what's the gridding thing happening? So you don't have grids on the other side, or it's you're just not showing the grids on the other side? Yeah, so this is a bit of a subtlety with the cylindrically symmetric mesh. So the cylindrically symmetric mesh, actually all we have is this right-hand side, right? And it wraps it around.
Yeah, but like all we ever store is just the right-hand side. We don't need to store the other side. And so under the hood, I'm playing a trick. So I'm just asking it to mirror the data. And I just didn't ask it to mirror the grid. That's all. So then here, what we're going to do is I've got receivers on the surface. So from 25 meters to 1,000 meters. And then we have sources. We're going to do 10 sources between 900 meters depth and 1,000 meters depth. So just like focused right around where this guy is. Set up a DC simulation, run, look at the data. There's just lots of plotting code. So here, just to show that like there is progress to be made, there's a difference between the background, which are the dots and the fraction. So like if we're starting from the background, we know that there's an improvement that can be made through the inversion. So in this case, I'm going to push the data pretty hard because it is a small target. We'll just do a standard L2 inversion right now. Tikhonov regularization and start with the background. And so it's a pretty quick inversion. Should be. So Sagi, just to bring you up to speed, we were talking about parametric maps. And so what I've been looking at, so you saw this issue where we have, because we're multiplying the arctan functions, it was giving strange, like it gives you these strange tails. We're multiplying them. And so in this case, I've replaced the way that we were doing the block, now approximating it with infinity norms. So much closer to how we treat the circle or an ellipsoid. If that makes sense.
I mean, your sensitivity is going to be way nicer, right? Because you don't have zero corners.
Yeah.
Can we rotate this?
I don't have that in there yet, but there's no reason we can't. Yeah. Another thing that sorry, go ahead, Joe.
Yeah, like inner product, field inner product. To rotate it.
Yeah. Yeah. We just need to add the angles in there. And Mike's thesis describes that too.
Slightly longer derivatives, I guess.
Yeah, yeah. One of the things that's also interesting is like, what I think would be kind of cool is to also allow us to invert for the epsilon value in the norm, because that actually gives you like how smeared the conductivity is. And so here, I'll show you what I mean by that. So here we have the P, we've got a strong slope, but if we have, I don't remember what the default is. So that gives you how smeared it is. So that could be an interesting thing to think about inverting for. Not implemented, might not actually be a good idea, but interesting.
What's the difference again between the slope and the epsilon? What in shape? What does it change?
So the slope is this guy here. So that changes how rapidly the arctan function drops off. The epsilon is changing how we're approximating the norm here.
Used to know who's inside or not.
Yeah, yeah. And so if you make the epsilon large, this rounds off. Whereas if yeah, it sort of softens how
It's a little bit like a tangent, but not exactly.
Yeah, I mean it's similar. So like we could sort of do it would almost be the same as softening the slope, but not quite, because as you see here, when I softened or when I increased epsilon, we didn't actually change the really the bounds of this guy. So something interesting.
I see.
Like is that a good number of epsilon to choose? Like I don't know, if I want to make sure, I always want to make it really long.
So one thing, what I have found is that, okay, so let's jump back to this and I'll come back to your question, Sagi. Okay, so we ran an L2, get a smeared out blob at the right depth. So that's good. And so Sagi, to answer your question, what I've found is that the best way to tune the parameters is to actually construct your mapping and then test it for a model that is about appropriate or like ballpark what you're expecting, and tune the parameters till you get second order convergence. So here, if we start with a moderate slope factor and moderate like softening of the corners, that should give us second order. If I crank up the slope, so let's make it.
Sorry, the P there was what?
This P is 5.
No, but what was? Is that?
It's like the norm.
That's the norm, basically. So that's going to control how round the corners are. It's still like, so here, if I show you this guy, so if we do, this is about the same scale as the target that I'm looking at in the other example. So here, if I do like P is 5, it's pretty square.
So this P is, sorry, I mean, ordinarily we think about, LP norms from, 0 to, I see, so from 0 to infinity.
Yeah,
okay.
So if I make this 1,
Okay.
it's an ellipsoid. Does that make sense?
Yeah.
Is that correct from L2 then?
Yeah, because I'm not taking the square root, just because derivatives are easier, but we can easily throw a factor of 2 if that's going to screw.
3.5.
We want to see the diagram.
Oh, I forced it to be an integer for now.
Okay.
There's no reason it has to be, but I made you put an integer.
And 0, do you get a delta function?
You get like a crop.
So you want to invert for P as well?
Well, it's a shape, right? Like so. That determines the shape, right?
Yeah, no, we certainly could.
Let's say you got a good sensitivity.
Yeah.
Not just a flaw, but the.
Yeah, no, there's no reason you couldn't.
Can you go back to your form of equation? So.
Yeah, so it is completely different.
So you just need to take the derivative.
Yeah. Yeah. So
we could let it pick. It's a plate or it's a blob.
Yeah. I'm not sure if that's a good idea or not, but it's
still a
absolutely
small
something we
space.
can try.
It's all
Yeah.
depends, right? Depends on the situation.
Yeah. Yeah. Okay.
You don't have to, I guess.
But so one thing I've found just playing around with it, if you make the P, so here in this case, when I made P5, like it's basically a rectangle. If you crank it up too high, it does, again, have trouble with derivatives. So Sagi, to answer your question, so this guy was second order. If we crank up the slope, so here it's 10 to the 10. If I crank up the slope, the derivatives are probably going to have a harder time. And you can actually already see that this guy's overflowing. And so like it is, it's just less stable. Hey, John. Hey, John. Yeah, okay, so this one actually worked out, but it's still, what I've found is if you make these parameters too harsh, it line searches like crazy. So you want to find something where you're getting sort of stable second order of whatever composite mapping you're doing.
I wonder if we can do like also like a cooling schedule, right? So you start with like really easy gradients, and then you try to reduce your factors to see the fit.
I don't actually know if that's necessary. I've sort of like, so playing around with it, if we set this to, we'll take a look at that. I found that as long as like you're sort of in the right ballpark, then it's okay. But it's really if you're just too harsh on those parameters.
It depends where you start, how far you start.
Yeah.
If you don't know nothing, then go on and let it move.
Yeah, absolutely. And so like we can run this inversion, and right now it's a lot slower. So like just taking a single step is a lot slower than taking an L2 step. I think some of that has to do potentially with just the mappings and the mapping derivatives. I think there's probably room to make those a bit more efficient.
Where's the time span in the forward, or?
I haven't.
Okay. Yeah.
But it has to be spent in the mapping stage, because the only difference between like this inversion and the previous inversion is my mapping. So I'd imagine the mapping derivatives.
This is great. This is way better than I think it's gonna be way better than before. Eh? It's a nicer parametric.
Yeah. And what I wanted to show too, so we can let that chug, but actually is, I've been working on the base class and trying to get that right. And there's a couple of interesting things that we can think about. So the base parametric right now, we have this slope factor, the slope. So I think I'm probably going to change the default and soften this just from my experimentation. This is too harsh. So you can see that if you provide the slope factor, it just scales it by the mesh so that you're getting something in the right range. Then all that the parametric really has is just a couple of things to like center you. So it's, just to deal with the active indices. Because right now, if I've got a mesh and I'm doing an EM inversion, so I have air cells, I don't want necessarily the air cells considered in the parametric map. So these are just to help you not have to worry about dealing with air cells. That's all. So it just grabs the active cells. That's it.
What do you need that?
Because so for EM, for example, I don't like my parametric map doesn't include. I don't want it to include air cells.
You can kind of like basically do a combo map, right? Start from all the main, use an active cell.
But then you would need to create another mesh for your parametric map.
That's true.
So like you could do either, but this is just, I didn't want to have to create another mesh.
Right. Yeah, so here you need to have a mesh.
Yeah, because we need to like be able to get our set of parameters onto a mesh, right?
Your slope you're only doing a single scaling, shouldn't be done cell by cell, because if your block gets close to the paddings or close to the bottom, your slope will not adapt, right?
At that point,
I mean, because the cell size is changing.
Mm-hmm.
it shouldn't. I mean, if you pick something that's going to give you a couple cells in your core region,
Or factor 2 in the out tree, right? It's going to change pretty quickly.
yeah, then in that case, like you might want to set the slope.
That's global. That's a single.
It's a single
slope.
scalar
Yeah.
right now. Yeah. I don't know. If it makes sense to provide a different cell by cell, because what would happen is you would like, so if you think about an octree, and if you're going from a very fine region to a coarser region, you're going to sort of smear it.
Yeah, you're going to increase the length of your.
Yeah. Yeah, that's something to think about. I don't entirely know, but for now it's a scalar.
So here, where's the maximum one? It seems like it's still out.
Yeah, so, well, we still are using the arctan. So we have to define a step function, right? So we define the function for the block. So I'll come to that, but this is just the base. This is the base class for all parametric maps.
Oh, I see.
So all that we need to have, like all that this guy has is basically coordinates and then some step function and its derivative. And so what's kind of fun is that eventually we can actually think about adding different types of step functions, like if that is something that people want to play around with. I know in Mike's thesis he used a hyperbolic tangent. I don't know if there's differences in convergence or whatever. So that's something that we could implement at this level, and then you could actually just have a keyword or a property that then says, I want, this, an arctan step function or a hyperbolic tangent, whatever. Yeah, so it knows about its, how to take a step function and its derivative.
Can you show me that where you're using the maximum?
Yeah. Okay, so that's the parametric block. So we've got it for 2D and for 3D. I have some thoughts about, because right now the order is sort of arbitrary. Eventually, I would like to actually allow the user to input something like a dictionary or a wire map so that you can have it in whatever order. But right now, you can't, which is okay. So here's the epsilon value and the p value. I think this is actually too high of a default. Having played around with it, at least for the casing meshes, it's probably too high. One of the things that I've been working with, and this is sort of looking forward for allowing users to input dictionaries or something like that, is a dictionary that just grabs the right parameter given a keyword. Because when I'm figuring out, for example, the derivative of the block, I just want to say, x naught of the block, rather than saying this is model parameter 2 or 4 or whatever. So Soggy, here's the echelon, that piece, and its derivative. And then to get a 2D block, for example, we just do 1 minus, and then x minus x naught divided by that squared. So then the full transform, we do the background plus, and then the difference between the background or the block and the background, and then times that arctan function. So that we take an arctan function, we lift it up to the value of the background, and then we say that this value up here needs to be equal to that of my block. Does that make sense?
Yes. So we still need to use the arctan function. Right?
Yeah, you still have to use an arctan function, but it's just a question of how it's being applied.
So which cells are in or out?
Yeah.
Now it's the full space that can be in or out, and not just what's in line with that block.
So you just remove the arctan for the block, to form the block, right?
Yeah.
You're just replacing that multiplication.
Yeah.
With the.
Yeah.
So to get in general case, we're still going to use some sort of arctan, whatever. What is that function?
Yeah, yeah. But what I've found like with this is that you want to design, so before, like when we're multiplying arctan functions, basically what we were doing is saying, I have an indicator of if I'm on the left, the right, whatever, and then we're just going to multiply those indicators together. So in this case, what you actually want to do is define one indicator that says I'm either inside or I'm outside. And then we take, we smooth the edges of that. And then the way I've done derivatives is I've actually broken it up so that here it is actually just calling individual derivatives for each piece.
Nice.
Because that's a little cleaner and it's like much easier to debug rather than just listing them all here. So here, if there's, what's nice, you can derivative test each piece independently so that if I see that it's not second order, you can go and make sure that the H vector that you're using to test, so say I see it's not second order and I suspect that this one's wrong, then the H vector I would pass would be 1, 0, 0, 0, 0, 0. And then that just tests, is this derivative correct or not? Does that make sense? And then you can go and see the derivative of the background and go double check that that line's okay.
So where did you set the M dict here?
So that is this guy here.
Yeah. So when that's called?
So I call that like here when I'm constructing the block, for example, is that rather than doing M of 0 or M of 1 to grab the right parameter, I grab it by a keyword.
Yeah, but my question is where that self that, oh, here, transform.
Yeah, so in the transform, I create the mdict and then I pass that to get block either 2D or 3D, depending on the dimensionality of the problem.
And that's where you're saying that you could pass, instead of M, you would pass a wire map or?
Well, so I don't actually think, I think the way we would change things is just like when you instantiate it, you would provide a wire map. So we wouldn't actually, like here, this would still be M. It still has to be M. But in this case, like when you instantiate it, the user then would have basically specified mdict. That's all.
You get a map times M and what's put it back.
Yeah.
And why not 1D?
A block in 1D.
Because then we could just move a layer, we could invert for a layer and just figure out what that layer is and how big that layer is.
Yeah, we could easily do 1D.
Because then it would be perfect. It would be like, you know, all the dimensions.
Yeah. Yeah.
We would use it.
Sure, we can easily do that. I mean, there is actually a layer already in there, and that actually uses the multiplication of arctan functions, which is okay for a layer because there's no corners. But we can easily adapt this to do 1D as well.
That sounds like a way more general function. Right?
Yeah.
Yeah.
Yeah. So that's kind of fun. And so this, what I think we could do is like, for example, for the circle map and things like that, we could actually just have those basically be this, but we specify the P so that we just have one function that we're always looking to. Circle or the ellipsoid, so. So it'll be a little bit before I get this actually like pull request ready, but that's sort of the idea.
It's the mother of all the parameters.
Well, and then like one of the things that's kind of fun that I want to try with this too is then using the sum map is using like invert for a smooth background and then basically specify here that I want the background to be 0. And then we're just adding some parametric blob on top of it. So that sort of allows us to do all of those kinds of things.
And about summing, what about summing parametric blocks?
Oh, like having multiple.
Because that's what Mike was going for.
That's,
That starts getting a little hairy with this.
I think that's a little bit better actually doing here rather than using SimMap, because the problem is when you're collapsing. Right?
Yeah.
So like using a multiple, like this arcan function, you could actually like define like when that happens, and we can actually define that value and go for it. Think about that's what Mike did. I think that's probably better, because like that's the problem of SimMap is actually when that's collapsing, right? So I think we had the same problem before. It's like you cannot really distribute exactly as you want. So again, you need some metric that's not going to happen, or when that happens, what's your treatment? That's I think that's a bit of a problem. Probably multiple ways, I guess.
Yeah.
No, but you're talking about actually incorporating multiple bodies.
Mm-hmm. But
Right,
yeah,
right.
exactly.
So my point was like when that body actually collapses.
Intersects.
So what's your choice?
Oh, I see, yeah.
Well, what would happen if you did it with the sum map is they would just sum.
Yeah.
So that's like if that's what you're looking for, then that'll happen.
But they would not
but-
be union. You want to be a union, not the
Yeah.
not the summation.
Yeah, so then that should be a separate map. Cool. I
Yeah.
think that was basically all that I wanted to show with that. So, yeah, and it is inverting, which is nice.
Very clever.
So,
So it doesn't care for the width of the anomaly. Eh?
well, this one I only let it go 3 iterations. It doesn't actually though, like, so with this problem specifically, we don't have great sensitivity.
Off the well.
Yeah, because it's like the source is in the casing, but the source actually, because it's in the casing, it smears out the currents. And then we have data on the surface. So what I found is if like you just really push this parametric inversion, it just tends to crank the conductivity of the block up without really moving the radius necessarily. It can sort of go, I mean, because we're not regularizing the conductivity, right? So it can just like start going through the roof, which is kind of interesting. So, cool.
Is that a resistor or not?
It's a conductor. You'd be really hard pressed to see a resistor in this setup.
If that's a resistor, it's not going to flow. Is that right?
Yeah, but the currents just go around it because the casing smears that out. So like you just don't have much sensitivity to it. Okay. Well, that's all I have at this point about that. Are there any questions, thoughts?
If you have another hole here on the side,
Yeah,
that makes it better.
not particularly actually, which is really interesting.
Oh, really?
Yeah.
Why is that? Like,
So is it injecting and receiving?
So right now I've got in current is downhole and we've got receivers on the surface
Oh.
and then our targets here. So
And then you're measuring the vertical field, right? Vertical potential and the other hole, if you are doing.
yeah.
So that's the problem. Like if you're measuring the horizontal field. Well, like there's a lot, like a.
Yeah, the horizontal field
Charge
could
hole
help.
up here.
Yeah.
The main response probably is correct. Be that much.
Yeah. And with this, I've also been working on getting fields derivatives for the DC code. Because right now we don't have like EX or, yeah.
Wow. We're not measuring EX. So. That's nice.
Cool. You okay?
Yeah, me too.
Perfect. So if anybody wants
When you say field derivatives for DC, does that also mean B field?
we don't have B fields hooked up.
It's a little bit more involved because you actually need to solve another system
Right.
Yeah.
What I was asking.
I bet that amazing hat.
Yeah.
Yeah, we do, like, it's kicking around, but we haven't hooked it up. Yeah. Yeah, but for this, because like I'll also move to time domain EM, I just thought I would deal with EX data to start with, and then we don't have to, like, there's less of a jump. So. John, do you want to take the wheel and talk a bit about?
Yeah, it's not going to take long, but yeah, I can. So I abandoned the initial PR, the tree mesh acceleration PR, because as we were talking with Joe and Thibaut, there was too much of a split. So instead, we'll just I just started improving the PFs, the potential fields on Thibaut's branch.
Okay.
And then as of last night, we're passing all the tests.
Excellent.
I know Thibaut's not here. No. So that's pretty good.
Which this is 670. Okay, cool.
This is this guy, number 617. And we're increasing the coverage by a fair amount, and that's mostly because I got rid of a lot of redundant code that we originally had. Before we had like a problem for the MVI and a problem for amplitude, and they were all separate. And I just collapsed it all into one, and now they're just cases. Amplitude, or if it's MVI, whatever. So it just reduces the amount of redundant code
Nice.
by a lot. And I added the switch for to use multiprocessing, so we can parallelize the forward calculations.
How are you parallelizing? Is that just the sensitivity computation? Or?
Yeah, just resistance calculations. Yeah. 1 second. I just created a subclass called forward, and it's creating a pool and just sending it to workers.
And that's okay on Windows now?
Yeah.
Never been an issue yet.
Okay, that's great.
Oh yeah, I guess it was an issue.
Yeah, because there was the name is
Right,
main, you have to protect.
Cannot run it in a notebook.
Notebook works.
Works?
Yeah, notebook works.
Oh, really?
But if you run a script, it needs to be protected.
Oh, okay, I see.
Yeah,
I thought like
Oh,
we cannot-
interesting.
we cannot run in a notebook. That's why.
it works in notebooks.
What was the Windows problem?
It's sort of if you don't protect your entry point, it starts to do a recursive thing, and it starts to restart a bunch of processes on all the nodes, on all the CPUs.
And that's using this multiprocessing?
Yeah, the multiprocessing.
I'll have to watch for that.
So when you you launch, I'm just going to show you an example quickly. Oops. You need to protect it in the main,
Oh, yeah, that's what we're doing.
right? And then if you just do this, then you're fine. You can just now it's just a parallel switch. And if you don't specify the processors, it uses half, because we found out that if you use all the processors, you're kind of swamping a system and it gets slower. Yeah. And then so I also put an example together. Yeah, I'm still running. It will come out soon, but basically the example is just it's a sparse MVI in a tree mesh, so kind of touching a lot of things.
Nice.
And as usual, my tests are kind of like all in one, so it's just making sure that the starting model and the inversion model are almost identical, and if they are, then that's the test. And then you touched everything. Joe, so what we're kind of like we're talking about last time is to be able to have the plotting function. It would be nice if we start a PR on discretize to be able to plot vectors on the slices. And I took I just took it apart and just slapped it in the example to create the mesh, right? So the mesh creation. 1 second, I'll find it. Yeah, to center it, basically just utils to center your mesh and your topography or observations, and then do the discretization. But yeah, I haven't spent much time working on the functions to do it, so maybe we could open a PR and start iterating if you want.
Yeah, I can do that. I know, like I said, Lindsay has the plotting pull request already on it. And if we could add on to that, I think it'd be acceptable, getting its plotting stuff.
Oh yeah, and we had the conversation with Craig too, right? To have the limits, the plot limits,
Yeah.
auto detected. That would be great. And then this is the example, just like a spherical smooth versus spherical. So a bit. And that's going to be it. So if you guys want to look at the PR, that'd be perfect.
And the mesh generation is in the discretized, or?
No, I just put it in here for now. I'm just not relying on anything to create it, right? It's just this snippet here. Find the extent, and then set where it is.
Oh, okay.
I think that's helpful to have in an example,
Right.
anyways.
Honestly.
Yeah,
Cool.
that's great.
Yeah, it's basically just figure out the limits of your topography, figuring out the center of it, the extent, and how far you want to get out, create the mesh. And then here, this was the function I was using to for a surface, right? To increase the paddings, increase the discretization around the surface down, but we can transform this into a function handle. Yeah. That's it for me.
Nice.
Is TICNAF working? Like a TICNAF regularization working with off-tree code? I think we actually played with it more, but I think we're not like before Joe's work. I think. Is that currently working, or
I haven't tried it.
are you using TICNAF?
I think it works. Been a while since we ran any of that stuff.
You're using off-tree code.
Not for the stuff I've been doing the last couple.
Oh, it's not in version.
Mostly for comments that I've been doing last week.
I had to update the examples for mesh creation, but that was pretty much the only one that was relying on tree mesh so far. So, but yeah, that's a good point because we don't have a Tikhonov example using tree mesh.
Pretty sure I did run one or two pretty good size examples though. I think I was using Tikhonov regularization and line.
With the latest tree mesh.
Yeah. Some of the new stuff was a lot faster.
Okay, so then we might be fine. But that's right, we should, because that would increase our coverage if we hit that part of the regularization.
I don't think the examples increase coverage, but if we have an example
test.
and then turn
Yeah.
it into a simple test.
Yeah.
Cool. Anything else people want to go over today? All right, sounds good. Thanks, everyone. Joe, anything from your end?
No, good. Just keeping up on what you guys are doing.
All right, sounds good. Perfect. Well, see you later.
Bye.
Have a good day.